Good morning, and thank you for the very kind introduction. So my name is James McNellis. I work on the Visual C++ team at Microsoft. I work on our libraries team, so I have spent the last few years working on our C standard library implementation and our C runtime. But I'm going to talk about that a little later today in my second talk, and today I'm going to give an introduction to a new feature that's being proposed for C++ called coroutines. So just as a show of hands, how many people here are familiar with what coroutines are? Okay, that's good. So before we begin, I just have a few notes. First is that the C++ coroutines feature is still in development. What I'm presenting here was the state about 2 to 3 months ago. I think there's been a few small tweaks to the proposal, but nothing major, so all the concepts are still the same. It's not yet standardized. There have been many proposals over the last few years for how to add coroutines to C++, but since this isn't standardized yet, it's not guaranteed that this is what it will look like. There's still a lot of contention in the C++ standards committee as to what coroutines should look like, but this is what most people are sort of converging towards, and this is what all three of the major compilers are at this point starting to implement. So obviously the Microsoft compiler, at least in the Visual Studio 2015 Update 2, should be able to compile all the examples that I have here. I know that we are working with Clang to get them implemented in the Clang compiler, and then I have heard rumors that GCC is also working on implementing them, but I don't know that firsthand. Yes, so with that out of the way, let's look, I guess, we'll start off with the motivation. So anytime you want to add a new feature to a language, if it's a new library, like that's kind of easy to add, right? There's not a whole lot of, there's a whole lot of thought that has to go into library design, but it's not at the same level that you need for adding a whole new language feature. And so if we're going to add a new feature to the language, it should either be really simple or extremely useful. And coroutines, it turns out, fit into that second category of being extremely useful. So I'm going to show the motivating example. This example comes from a colleague of mine, Gor Nishanov, who is heading up the coroutines design work. So he's the main author of the specification, and he's the main implementer in the Visual C++ compiler of the coroutines feature. So this is an example that he's given in several talks that he's given on this subject, and he let me steal it for my presentation. So here we have a synchronous program. And we have this function, TCP reader, and it's going to go and open a TCP connection, and then it's going to loop, and it's going to read some data from that connection, and then it's going to return the number of bytes that were remaining, or that it should have read that it didn't. And ideally, we'd probably be doing some work with the data in this loop, but we're just trying to show, this is the synchronous process. And because it's synchronous, that call to TCP connect, it's going to block until the connection is established, so it's going to block on network communications. And then every one of those calls to the read function is going to block as well, waiting for the read to complete. And if the network connection drops, that might block for a very long time. So since these operations may take a long time, we don't really want to block, right? Like if we're on the UI thread, we don't want to block the UI and have it ghost and become unresponsive. And if we're on a background thread, we don't want to sit there using up the background thread for no reason when that thread could be doing other useful work, if it's a thread pool thread or something like that. So what we really want to do is we want to tell the machine, hey, go establish this TCP connection, and when it's established, call me back so that I can use it. And then, hey, go read this many bytes from the connection, and when you have them, call me back so that I can use them. And to do that, we're going to have to make a few small changes to this code. So let's assume for a moment that we have an asynchronous TCP library as well. So it has functions that basically allow you to connect, and then you provide a callback of some form, or it provides a way for you to register something to be done when operations are completed. So here is our new function. So you'll notice the first thing that we've had to change is we can no longer return just an integer, we now have to return a future of int, because when this function returns, we're not going to have the actual result. We're going to have to provide a way for the caller to get the result from us, but we won't have it when we return. Next, we're going to need to wrap up all of our state into a structure so that we can pass it through all the asynchronous operations. So here I've written a little reader state class, and it's going to have that buffer that we had, and the counter that counts the total number of bytes remaining, and then the TCP connection. And we'll just make an instance of that the first thing we do when we enter this function. So then we'll establish our connection, so we'll have our TCP connect, and we'll assume that that returns a stood future of TCP connection. Then inside of that, the continuation, so this continuation will run when the connection is established. We'll store the connection in our structure so we can access it from future continuations. And then we'll start a loop. And in this loop, we will we'll do our read. So here we establish the read, and then we'll have a continuation after that. And then for each read, we'll do the processing of the data. Now, there's still even a little bit of magic here, because we've got this do-while function, which we haven't explained, but that's still rather easy to implement. But even so, is there anybody here who thinks this code looks just as simple and is as easy to write and understand as the previous example? Anybody? Oh, yeah? I made the mistake of raising my hand when Gore gave the talk, and then he gave me a hard time, but it was in jest. Okay, so there's just one little problem here. There's a bug in the code. Would anybody like to point out where the bug is? Okay, I didn't think so. So in the original example, we returned the total number of bytes, right? And here we are not returning the total number of bytes. Does anyone want to guess what we have to add where in order to return that number? Yeah. So basically we have to have yet another continuation that when that do-while loop is finally finished, we're going to call make ready future to make a future that contains that state. So this example should be the asynchronous equivalent of the original example. And obviously this is much more difficult to write. There was a bug there, and it was very difficult, to even see that there was a bug. And debugging this is going to be a total pain. We have a lot of code that looks like this nowadays because, there's this big push toward asynchronous operations. This kind of code, you get a crash dump with some call stack deep inside of, .then, and it's like I fill with terror. So let's see what we can do to make this better. Well, we could try, implementing this as a state machine. And so, we can think of this function as being a state machine. And so first we enter into a connecting state where we call TCP connect. And then we enter the reading state where we have that read loop. And then when that read loop is done, we enter the completed state. We're done. And so we could write this out as a class. And so here we've got a TCP reader class, and we have those same data members that represent those local variables that we had. And then we have some member functions that represent each of those state transitions. And then we can implement those member functions. So here's 2 of them, and the other 3. Has anybody written state machine code like this? I think it's fairly common in a lot of systems to write code like this. But that's still a lot more code than our original example, and it's still not nearly as easy to look at and guarantee, yes, this is correct, right? It's very easy to make mistakes with code like this, like accidentally calling, transitioning into a state that you're not allowed to transition to from a certain point. So I guess if nothing else, this will give better, more debuggable crash dumps than the original asynchronous example we have. So what if? That was all pretty horrible. And our asynchronous code sort of ended up looking a lot like regular expressions, right? You might be able to write the code that does the right thing, but you'll never be able to maintain it or modify it or make changes to it over time. So what if we had code that looked exactly like our synchronous version, but it was asynchronous? So this is our synchronous version of the code with a little bit of white space added. And the asynchronous version with coroutines looks like that. So it's basically the exact same, and I'll highlight the things that I've changed here. So we've changed the return type because, again, we don't have an int to return to the caller. We only have the future of int. We have this co-await on the TCP connection and a co-await on the read, and we'll explain what those are in a minute. But basically, those are the points at which we suspend execution of the function until we have the data that we're ready to proceed with. And then we have this co-return, which is like a return statement, and it returns the value through the future to the caller. So we're going to actually, by the end of this talk, we'll be able to implement all of the library machinery that is required to make this work, and we'll understand all of the compiler machinery that's under the hood to make that work. So how many people think that this is simpler and better than either of the two asynchronous examples that we looked at? Oh, okay, so that's everybody. I'm glad to see that. All right. And by the way, if you have any questions at any time, please feel free, just raise your hand, and if I don't see you or I'm ignoring you, just shout out or something. So let's look and see how this works under the hood. So let's start with the basics. What is a coroutine to begin with? Does anybody want to give a basic definition of a coroutine? No. Okay. So a coroutine is a generalization of a subroutine. Does that clear it up? All right. So what's a subroutine? So a subroutine is something that can be invoked by a caller, so you can invoke a subroutine, and when it's done, it can return control back to its caller. So basically a subroutine is, in C++, it's a function, right? You can call a function, and when it's executing, and then when it's done, it returns control back to its caller. So a coroutine also has those properties. It can be invoked by its caller. As we saw previously, a coroutine just looks like a function, and it can return control back to the caller via what we saw, the co-return statement. But a coroutine also has two other properties. A coroutine can suspend its execution and return control back to the caller without completing. And once it has been suspended, it can return, or the caller can resume execution of the coroutine, and it'll pick up where it left off. So it's a lot like in our state machine where we could, transition from one state to another. Suspension points are basically where you transition from one state of the coroutine to another. So in the C++ coroutines proposal, both subroutines and coroutines are functions, and a function can be either a subroutine or a coroutine, and we'll see what distinguishes them. So I have this handy little table that we'll look at. So both subroutines and coroutines can be invoked, and they're invoked via a function call, so we just call f. It's the same for a coroutine and for a subroutine. We can return from a function using the return statement, and we can return from a coroutine using the co-return statement, and we'll see why that needs to be different. And then to suspend a coroutine, we use that co-await expression, so that's how we suspend execution. And we'll fill in this table a bit more as we go along. So what makes a function a coroutine? If we see a function declaration like this, so this compute value function, is it a coroutine? Maybe. Someone in the audience said maybe. That is the correct answer. Maybe, maybe not. Whether a function is a coroutine is an implementation detail. So it's not a part of the type of the function. The caller doesn't need to know if it's a coroutine or not. It has no effect on the declaration at all. So what makes a function a coroutine? Well, a function is a coroutine if it has a co-return statement, a co-await expression, a co-yield expression, which we have yet to see, or there's also a range-based for loop that uses co-await. But in short, a function is a coroutine if it uses any of the coroutine support features. So when the compiler is compiling your code, if it's compiling a function and it sees, oh, hey, this function uses one of those things, it has to go and switch from I'm generating code for a subroutine type function into a I'm generating code for a coroutine type function mode. So here is an example of that compute value function. You can see here on the left, we have a version, and this is just a normal function. It calls std async and returns the future that's returned from it. And then over here on the right-hand side, we have a version of the compute value function that uses co-await and co-return. So these do the exact same thing. In this right-hand version, we call std async, and we await for the result. So we'll suspend execution, and we'll get basically, we'll attach a continuation. And then when we have the result, we will store it in that future to make it available to the caller. And we'll look at this in more detail in a bit. All right, so what does that co-await thing do anyway? So here's its form. Basically, you can have an optional result that you get out of the co-await expression, and then it just takes an expression. And what the compiler expands this to is this. So the co-await is used to suspend execution of a coroutine. So the expression must have some awaitable type, and we'll see that on the next slide of what that means. And so the first thing that we do is we check, is the thing that we're awaiting already ready? If we already have the result we're awaiting for, then we don't need to suspend. If it was not ready yet, then we call await suspend on the thing to enable custom pre-suspension action. And then there's a suspend resume point, and this is where control is returned back to the caller. When the coroutine is resumed then by the caller, and we'll see how that works, it resumes execution there, and it calls this await resume function to allow you to customize the resumption behavior. So from that, we can see that in order to be awaitable, a type has to support 3 operations. Await ready is called to determine if we need to suspend at all. Await suspend is called just before suspension in order to enable custom pre-suspend logic. And then await resume is called after a coroutine is resumed to retrieve the value. So let's look at a very simple awaitable type. So this is the simplest one, and this is part of the library that's being proposed with the coroutines proposal, and it's called Suspend Always. Does anybody want to guess what a type named Suspend Always will do? Yes, it always suspends. So if you await something of type Suspend Always, it will suspend execution of the coroutine. And you can see that we do that by just returning false from await ready. So in that if statement, we'll check, is the thing ready? No. We'll call the await suspend, which is a no-op. We don't need to actually customize what happens when we suspend. And then we'll reach that suspension point, and it'll just suspend execution of the coroutine. Then when we get resumed, we also don't need to do anything there. There's no magic that we need to do when we get resumed. So that's also empty. So here's a simple example. So in this coroutine, if you call it, it'll print out my coroutine is about to suspend. We co-await on that suspend always, and this will suspend execution of the coroutine, return control back to the caller, and then if and when the caller resumes the coroutine, it'll print out my coroutine was resumed. Cool. So there's one other really simple awaitable type that we can look at. Suspend Never. Does anybody want to guess what this type does? Yes, it doesn't suspend. So we return from await ready, we return true and say we already have the value. And so what this allows you to do is anytime you await on a suspend never, it's basically the compiler can eliminate that. You're not doing anything at all. We'll see this is mostly used for implementing other awaitable things or for implementing promise types, and we'll see how that works. We'll see how this is used a little later. But basically this function, if you call it, it'll immediately print out my coroutine before the no-op await. It'll do the co-await, which is a no-op, and then it'll immediately print out my coroutine after the no-op await. It will never return control back to its caller until you reach the end of the coroutine. So that's the first half. When a coroutine is executing, it uses the co-await to suspend itself and return control to its caller. So how does the caller resume the coroutine? And to answer that, we're going to have to look at what happens when you invoke a coroutine in the first place. So to look at that, we can start by looking at what happens when you invoke a function. Well, when you invoke a function, the compiler has to construct a stack frame, right? I mean, I know there may be someone in here who's thinking that, okay, C++ doesn't have any concept of stack frames, and that's a machine thing, but we're talking about real machines here today. So the compiler is going to, or the compiler has to construct a stack frame, right? It has to have space on the stack for the arguments and the local variables and the return value, and storage for any volatile registers if you make function calls. And so, the compiler will generate code that knows where all these things are on the stack so it can find them later. And when you invoke a coroutine, it's going to do the exact same thing. It's going to create what's called a coroutine frame that has room for all the formal parameters, all the local variables, selected temporaries if there's any temporary expressions that may need to survive across a suspension point. It also has to be able to store the execution state for whenever the coroutine is suspended. So if there's any registers at all, even non-volatile registers that the coroutine uses, those obviously need to be stored before it returns control back to its caller. It also needs, notably there, it needs to be able to store the instruction pointer from the point at which the coroutine was suspended. And then finally, it needs to store the promise that's used to return a value or values back to the caller eventually. And we'll look at that one in a bit more later. In general, this coroutine must be dynamically allocated, because once a coroutine suspends and returns control back to its caller, it loses all access to the stack, right? I mean, at that point, the caller can go call some other function, and it's just written over all the stack space that the coroutine was using. So in general, the coroutine has to be dynamically allocated. By default, operator new is used, but that behavior can be overloaded for specific coroutine types to allow allocation customization. This is especially important. One of the most important pieces of the coroutine specification is it works both in code that uses exceptions and code that does not use exceptions. We wanted to be able to use this in operating systems code or really old legacy code bases where we can't use exceptions, and so that's why it supports some of these customization points. Creation of the coroutine frame occurs just before the coroutine starts running. So you call the coroutine and you get to that opening brace of the coroutine function, and that's where the compiler injects the code to create the coroutine frame. And it's just, in that way, it's just like the stack frame for an ordinary function. And then finally, after it's constructed all this, but before it starts actually running code inside of the coroutine, the compiler returns a handle to this coroutine frame to the caller of the coroutine. And that handle is the key to how the caller and the coroutine communicate with each other. So what does that handle look like? It is, interestingly enough, called coroutine handle. I don't know what namespace it is in right now. Eventually it'll be in namespace std, once it's formally standardized. But there's two forms of it. So the first form is a specialization for void, and so this is the type of coroutine handle that is used when you have a coroutine that does not return a value back to its caller. And the second type is basically specialized on promise types. So for each specific promise type that you have, there's a different specialization of this. And it's derived from the coroutine handle for void because it supports all of the things that coroutine handle of void supports, plus a couple other things. So we'll start by looking at the first version, the coroutine handle of void. So what do we need to have, the compiler provides this, or this is provided as part of the standard library for use of coroutines. So what does this coroutine handle need to have in its implementation? Well, it's possible to have an empty coroutine handle, which is a coroutine handle that does not refer to a currently running coroutine. And so we allow it to be default constructed, in which case it just has an empty state. We allow you to construct it from nullputter, which has the same result. We allow you to assign nullputter to it, which basically just resets it to be an empty coroutine handle. And then it's explicitly convertible to operator bool, which just means that you can test it in an if statement to see is this coroutine handle valid. Second, the coroutine handle provides conversions to and from void star. So the reason that so basically you can call toAddress and it'll give you a void star that represents that coroutine. And then later you can take that toAddress and pass it to fromAddress and it'll give you the coroutine handle back. And the reason that this is really useful is that a lot of old APIs, for example, thread creation APIs or thread pool APIs, when you pass them a function pointer, you also get to pass them a void star that represents, some context that they will call your function with. And that way, when you start a new thread, it allows you to, pass some information to that thread to start with. So this allows you to basically smuggle or, pass coroutine handles in through legacy APIs like that. So third, the coroutine handle provides a way to resume execution of the coroutine. So this is what we were looking for. It has a resume function, and if the caller calls this, then that will cause the coroutine to be resumed. And then there's a function call operator, and that basically does the same thing as resume. The coroutine provides the ability to, or the handle provides the ability to destroy the coroutine before it finishes executing. This will cause all the local variables to be destroyed, just as if a return statement were evaluated at the last suspension point that was reached in the coroutine, and we'll see an example of that in a minute. And fifth, the coroutine handle provides a way to test whether the coroutine has completed execution. So this will return false if the coroutine is currently suspended. It will return true if the coroutine has reached the end, either via a co-await or by reaching the end of the coroutine. So that's the specialization for coroutine of void. And the coroutine that that works on other promise types, so for coroutines that return a value back to their caller, they have a couple extra operations. So they have all those operations from before because they're derived from coroutine of void or coroutine handle of void. They also provide a promise function that returns whatever the promise is for that coroutine. And it provides a conversion, so if you pass in a reference to that promise, it'll give you the coroutine handle back. So with that out of the way, let's just build a really simple coroutine. I guess before we do that, are there any questions yet? Yes?
Those two step methods that are built into coroutine handle and the specialization. And those means that there is some kind of state stored inside the coroutine handle class, because those are static functions. And how can I retrieve a coroutine handle from a void pointer, for example?
Yes. So
Some state stored somewhere.
Yes. So the question is, so this from address function is a static function, and so it does not have a this pointer. So the question is, how does the coroutine have some state inside of it to make this happen? And the answer is yes. So a coroutine handle will generally have a pointer. It'll usually be a pointer to the actual coroutine frame, right? So we saw on the previous slide, the compiler has to generate a coroutine frame, and we'll see that in the next few slides. And it's going to dynamically allocate that generally. And then the coroutine handle will just be a pointer to that coroutine frame. And that coroutine frame will continue to exist until the coroutine is destroyed. And so when it does this from address, oftentimes it's just saying, okay, I'm going to reinterpret that void star as if it were a coroutine handle. The same thing works with the from promise function. So if you give it a reference to the actual promise that's being used for the coroutine, then it will... it knows what the offset of the promise object is inside of the coroutine frame, and so it will, it'll just calculate the correct address of the coroutine frame from there. Does that make sense?
Yeah. Okay.
Excellent. All right. So I think the easiest way to demonstrate all of this is to build just the simplest coroutine we can. So here we have a coroutine function called counter. And when we invoke this function, we're going to print out, okay, just let everyone know that we called. And then we're going to loop forever. Each iteration through the loop, we're just going to suspend execution. And then when we get resumed, we'll print out we were resumed, and this is the index that we were resumed at. So here's a little program that uses it. We'll see main will print out saying that it called itself. There we go. We will then construct the counter. That will cause the counter to start execution. It'll print out this statement. It'll enter the loop, and then it'll suspend. So then the next thing that will happen is main will resume execution here, and it'll print out main resuming counter. We'll then resume the coroutine twice. So the first time, it'll print out just saying, hi, I've been resumed, and I was resumed the first time. The second time, it'll say, hi, I was resumed, that was the second time. And then finally in main, we'll just say, okay, now we're done. So you can see here how we enter and leave control of the coroutine. But you can see that, because we're keeping that count, it's actually maintaining that state, right? It knows what that I value is. So the thing that we need to look at here is how do we implement this resumable thing so that all of this works? So we need a little bit of code here. So the first thing we need to do is we're going to need to have what's called a promise type. And this is the type that tells the compiler how we communicate back and forth with the caller. And we'll look at that definition on one of the future slides. The second thing we're going to want is we're going to have a member variable that just stores the coroutine handle. We're going to have a constructor that allows you to construct one of these resumable things from that coroutine handle, and it just stores the coroutine handle. We'll have a destructor that destroys the coroutine. Since this coroutine runs forever and it never returns, we need to have a way to destroy it because it'll never reach the end of its execution normally. We'll provide that resume function that we were calling, and this allows you just to resume execution of the coroutine. In general, when you're implementing types that are designed for interoperation with using coroutines, you won't actually write an explicit resume function. This is just for exposition demonstration purposes. So then we'll also need a bit of boilerplate, because what is good C++ without some boilerplate? We want this thing to be default constructible. We do not want it to be copyable because we own that coroutine handle, and we don't want to have to deal with reference counting or anything like that. But we do want it to be movable, so we'll just have a move constructor and move assignment operator, and they just copy the coroutine handle into ourselves and then reset the one that's being copied from. So this allows us to move these things. So then we'll need to define that promise type. And here again, we need some operations that are required in order for a thing to become a coroutine type. So the first thing we need is a getReturn object. And this is how we bind from that promise type back into the resumable thing. So basically, and we'll see this in a moment, the compiler will call this to construct the resumable thing for you. And we can see it do is we just call the resumable thing constructor, and then inside of it, we use that from promise function, so we know that the this pointer is the promise for the coroutine that's being constructed, and we get the handle through that. We have to provide these two functions called initial suspend and final suspend, and we'll look at those in a minute, but in this coroutine we suspend never. And then we need this return void function, which is what happens if you do a co-return from this function with no argument. So, back to this coroutine code. When the compiler sees this function, the first thing it's going to need to do is it's going to need to create some structure to store all that state we talked about before. It's going to need to create a structure for that coroutine context. So here's the bare minimum. We know it needs to contain the promise that we're going to use to pass back the coroutine handle to the caller. We know it's going to need to contain that I, local variable. And we know it's going to need to contain the instruction pointer so that when it suspends execution here, when you go to resume it, the compiler knows, aha, here's where I resume execution at. And then the compiler may have to generate storage for registers or anything else that it needs to use inside of this function. So then the compiler is going to take this, and it's going to have to generate some extra code for us. And the code that it's going to generate, first, is at the very beginning of the function. It's going to construct a new instance of that counter context. It's going to initialize it however it needs to initialize it. It's then going to call getReturnObject in order to get the resumable thing that it's going to pass back to the caller. And then it's going to call that initial suspend function, which basically, again, just allows you to have a way to suspend execution of the coroutine before you enter the body of the coroutine. Then at the end of the coroutine, it's going to call that final suspend. So that allows you basically to suspend execution of the coroutine before the coroutine actually gets destroyed automatically. So we can see we've got this nice new here to construct the coroutine context. Where does the coroutine get destroyed? And where does that get deleted? And the answer is the first of either when you reach this final suspend label, so here after the final suspend completes, there will be an implicit delete statement there, or when that coroutine handle destroy function is called to destroy the coroutine. Are there any questions about this example? Okay. So we can make some small changes to this to show that you can actually have coroutines running concurrently, we'll see. So here we have a new named counter. So this is just like the counter we had before, but it takes a local variable, or it takes an argument named name. And basically, every time it prints out, it also prints out its name. And so here, in our main function, we now construct two of these counters. We construct counter A, which is named A, and we construct counter B, which is named B. And then we resume them each at different times, and I've colored them red and purple so we can line them up with the output. But we can see that the A counter is constructed first, and then the B counter. And then we resume the A counter, and then we resume the B counter twice, and then we resume the A counter again. But this shows that once a coroutine has suspended, you don't have, resuming it does not need to be the next thing that you do, and different instances of the coroutine that you called are independent, right? So both of these, counter A and counter B, have their own coroutine state. They both have their own local variable I. They don't conflict with each other. So with that, we now know, we can fill in this bottom square here, that the way that you resume a coroutine once you've suspended execution of it is to just call resume on the coroutine handle. All right, that's all well and good. But ideally, we'd also like to be able to return things from a coroutine, right? So in our initial example, we had the co-return on the integer so that you could return, fill in a std future. And so let's see how we implement something like that. So back to our compute value example. First off, why is it a co-return instead of a return? And the second interesting thing here is result is of type int, but this function returns a future of int. There's no implicit conversion. You can't assign an int to a future of int. So there's some magic going on here. And the magic is inside of that promise type. So we've already seen this first promise type example, and it's the way a promise type needs to look for promises that don't carry values. And you know that because it has a return void function that is called for a co-return with no argument, or when you fall off the end of a coroutine. In coroutines that return values, like this std future example that returns a future of int, you have to provide, instead of return void, you have to provide a return value. And this is called for co-return when you have a co-return with an argument. So here, we'll look at the future example in a minute, but here's just a simpler example that shows the use of co-return. We have a main function that calls this getValue. Sorry, I made some changes to the slides last night and sometimes can't remember. Okay, so what really happens inside of this getValue function? Well, the compiler is going to have to generate all that same boilerplate that it did before, right? It's still going to have to construct the coroutine context. It's still going to have to call getReturn object and do the initial suspend. And it's still got that final suspend label, and it awaits on the final suspend. We already know what that co-await is going to do. So what does that co-return do? Well, the compiler just takes that and transforms it into a call to that return value function. So it's going to get the promise from the context, call return value, and then it's going to go to the final suspend label. Now in this example, the final suspend label is the next thing, so that goTo doesn't actually do anything, but you can have co-return statements anywhere inside of the coroutine, just like you can have return statements anywhere inside of a function. So now that we know that for our resumable thing, we're going to need to make a few little updates. So first, we need to add three things. First off, to the promise type, we need to add a value, right? We're going to need some way to store that value until the caller asks for it. The second thing, we're going to need to provide a return value function that takes the value. The compiler is going to call this with the value that you passed to the co-return, and then does something with it. In this case, we want to store it inside of that member variable. And then the third thing, and this is just for our example purposes, is we need to add a get function to our resumable thing so that we have a way to get the value out just so we can print it. You can see that we're calling that here. So let's walk through our little example here. So first, main prints, I'm calling getValue. Okay, great. We're inside of the getValue function. We print out, great, getValue was called. And then we suspend. Then in main, we print, control returns to main, and we print that we're resuming getValue. And so we call resume on our resumable thing, and we re-enter control of getValue, and we print out getValue resumed. We reach the co-return type, or co-return function. The compiler will, or the code that the compiler generates will call that return value function. It'll set the return value to 30 and return control back to the main function. And then in the main function, we'll say main value was, and we'll print out the value that was returned, which was 7,059,560. So that's perfect. Any questions? Okay, what just happened here? We have to look at the coroutine lifetime. So I said a little bit earlier that a coroutine is destroyed when the final suspend is resumed or when the coroutine handle destroy function is called, whichever happens first. And so basically it's going to be destroyed here when we reach this point in the function. So as you can see, our final suspend does a suspend never. So when we get to this co-await statement, that's a no-op. It's the final suspend. And then that's when the coroutine gets destroyed after that. So if we look at our promise type, we have to make one small change here to make this program work. Does anybody know what that change is? Okay. So we just have to change final suspend to be suspend always. Right, so now we'll reach that final suspend label. We'll await on that suspend always, which will suspend execution of the coroutine without destroying the coroutine. And so now if we run the program with that change, we get our value back. But here, now when is the coroutine destroyed? Because we we now have suspended execution of the coroutine and we've stopped using it. Well, it's destroyed when the resumable thing is destroyed, because we had this in our definition that we had earlier. So in the destructor of the resumable thing, when it goes out of scope, it calls destroy on the coroutine. So how does coroutine destruction work? Well, it's actually just like destruction of local variables work in a function. So the coroutine will destroy all of its local variables in reverse order, just like when a function returns. So here, yes, we can pretend we have a type named print when destroyed, and it'll just have a cout in its destructor that prints out a message saying that the object was destroyed. And so here we can see that when the coroutine is destroyed here at the end, it'll print out B destroyed and then A destroyed, because B will be destroyed before A. But what happens if, so here in this updated main function, we don't resume the coroutine, so it gets stuck here at this first co-await. Which local variables will get destroyed? Well, it's just like in a function, in a function, if you have a whole bunch of local variables and somewhere in the middle of them you return, it's only going to destroy all the local variables that were constructed up till that point. So in this example, it'll just print out A destroyed, because B was never constructed and won't be destroyed. And the compiler tracks this through the instruction pointer or a state table or something like that that it generates into the coroutine context. So just a recap of the coroutine lifetime: the coroutine is destroyed whenever the final suspend is resumed, or the destroy function is called, whichever happens first. And then when a coroutine is destroyed, it cleans up all of its local variables, but only those that were initialized or constructed prior to the last suspension point that was reached. Great. So those are our basic examples. Are there any questions about them? Yes?
Go back to the example of the get value. What would happen if instead of a call return 30, you would just put return? I presume that the compiler already knows that get value is a coroutine and is not. Oh, thank you.
Yeah.
Told us at the beginning that as soon as the compiler sees a co-await instruction, understands that is not a subroutine but it's a coroutine. So why putting co-return, which is just confusing things, instead of a normal return?
Yeah, so that's actually a good question. And in early versions of the proposal, there was no co-return statement. It was just return. So you would use, at the time it was just called await instead of co-await. I guess as a sidebar, the co_ prefixes were added to avoid ambiguities with existing code. They didn't want to break existing code that may have a local variable named await. So that's how we ended up with co-await. The reason that we have a different co-return is to allow you to have coroutines that never await, right? So for example, if we wanted a function that returns future of int, right? And inside of it, maybe inside of some overload of it, we don't actually need to await for anything. We could just call co-return 30, and it would automatically handle the conversion to int.
Sorry, but a coroutine that never awaits wouldn't be just a subroutine?
It would, yes, it would be a subroutine. This allows for, basically it just allows for more general syntax. I don't think there's a particularly good reason. I think that there was mostly just a lot of, there was a lot of interest in having the, well, I take that back. So there was one concern about compilers that do single pass parsing, that they wanted to make sure that, like, say you reach a return statement and then later you see a co-await. Like, now you've got to go back and start over, processing the function again. And now if you always have to use a co-return instead of a return, then the case where you have a return statement followed by a co-await is it's a syntax error.
Right. Okay.
But like in general, you could make it work with just the return keyword. Yes.
Can you go back to the slide with the go-to label? Okay, we have this final suspend label here. We need this because we can have multiple return points.
Yes. Yeah, so the reason that the reason that here we have a go-to final suspend label followed by the final suspend label is that, yes, you can have multiple co-return statements within the function, just like you can have multiple return statements inside of a normal subroutine function. So in this case, that go-to is a no-op, and the compiler won't generate any code for it. But if we had, like up here somewhere, we had, and if the argument isn't right, then co-return some error value, then that go-to would have effect.
Okay, thank you.
And I should note these labels, like they're compiler internal. It's not like you can write a go-to that, go-to final suspend label, though I'm sure none of you here would consider writing go-tos in your code. All right, so those are basic examples, but how about something that's actually useful? Let's look at std future. So std future is a really example because we have to implement both sides of this contract, right? We have to implement the promise type. We have to provide the bindings to allow the promise type to be awaited on, or to allow us to have a coroutine that uses that promise type. And then we have to have a way to make the async, so the std future that's returned from that, be awaitable so that we can await on that result. So obviously this use of std future is very silly, and there's easier ways to implement it, but we don't really care what the contents are, we just care about the machinery that go around it. So let's start by implementing the promise type for std future. So we'll open up our standard library future header, and we'll add a promise type to std future. And well, we can't do that because we'll pretend like you are not. I'm being told I have 10 minutes left. We don't want to do that because we'll pretend that you're trying to implement this just for fun, and so you don't want to have to modify the future header yourself. So there's another. We could do this, and when we're implementing it in the standard library, this may be what we do. But you can also implement the things you need through a specialization of something called coroutine traits. So the coroutine traits are how the compiler finds the promise type given a particular return type for a coroutine. And so the default template for this, the primary template, it takes everything that it isn't specialized for, and it says the promise type is whatever its promise type def is. And so in the previous examples where it was an actual class, it'll just be that. But we can also specialize coroutine traits to have a particular promise type that we want. So for std future, we can do this by specializing coroutine traits for future of t. We'll just ignore the arguments. Those are used for other extensibility that we won't be able to get to in this talk. And in our promise type, well, we need to store the std promise, which is the way that you communicate between an asynchronous operation and the std future that represents its eventual value. We will have our getReturn object, which allows you to convert the promise into a future to be returned to the caller. And we do that, we just call getFuture, which is a member of std promise. Our initial suspend and final suspend, they don't suspend. We don't need to suspend execution of the coroutine. And then our return value, we just call setValue with whatever the value is that we're trying to return back to the future. And then finally, coroutines, we haven't mentioned this yet, but coroutines also provide a way to basically eat all of the exceptions so that you can wrap them up to return back to the caller. And so we will have this set, we will implement this set exception function. It's optional. And in there we get a std exception pointer with the exception that was thrown, and we can set that in the promise as well. And so this works with the existing std future exception machinery. So That's the promise side of it. With that, we can return a stood future from a coroutine. But now we need to implement what we need for the co-await. So for that, we can go and open up our future header, and we can start adding some member functions to it. But we don't want to do that, because again, we don't want to modify the header. We could do that. Instead, what we'll do is we can actually just implement all three of those functions, the await ready, await suspend, and await resume, as non-member functions. So they allow extensibility that way. So in our await ready, we just call isReady on the future and ask, are you ready? Do you have the result for me? In await suspend, we do something interesting. So in await suspend, we get the future and the coroutine handle. This would be the this pointer if this was a member function. And what we do is we take the future and we say .then. So when the future is done, then run this code. And inside of there we have a lambda, and it gets passed in, the future passes itself into that. We have the lambda capture the coroutine handle and call .resume. So what this means is that whenever the future that you're waiting for finishes executing, it'll automatically call this continuation and resume execution of the coroutine. And then in await resume, so when we need to resume execution, we just call get to get the value from the future. If the future has already completed and run the continuation, then this will not block. But if the future has not yet completed, then this will block until the operation is completed. So I'll admit we cheated a little bit here. Stood future does not have isReady or .then functions, but stood experimental future, the new version of stood future, does. So if we look at compute value once more, like that, those are the two things that we need to implement. Any questions about that example? I have 5 minutes left, so I will go through the one last section quickly. So that's all the basics on coroutines. There's one other feature that we'd really like to implement, or that we'd really like to be able to support in C++, or I guess I should say there are a lot of other design patterns that involve state machine transformations that we'd like to be able to support in C++, and coroutines enable us to implement a lot of those. And one of them is the iterator pattern, or yielding. So is anybody familiar with C# iterators, where you have the yield keyword? Yes, so we can actually implement that using C++ coroutines through one last keyword, co-yield. So what we do here is I've defined this little integers coroutine, and it loops from the first integer to the last integer you pass it, and then in each iteration through the loop, it does a co-yield to yield the value back to its caller. This is basically like returning the value, but not completing execution of the coroutine. So it's like as if it was calling set value and then suspending execution. So then in the main function, we can say for each integer in that range that we're yielding, we can print out the integer. And I should say there's no magic in this range for loop. Oh, yeah, that would be the result. There's no magic in this range for loop. We could say, we could turn it into a normal for loop that it's, we create a local variable named the integers, and then we iterate over them, and we'll define how these begin and end functions look in a moment. So what co-yield does is the compiler just takes the co-yield and it calls it into a co-await, and then it calls yield value on the promise. And so basically yield value is like that set value that we had before, but it's for yielding instead of setting the final return value. So if we want to implement our int generator that we had before, well, I guess we had generator of int before, but I've made it not a template to avoid angled brackets on the slides where possible. So we'll have our getReturn object, which does what we've seen before. Our initial suspend and final suspend will suspend always, right? So when we create the generator, we don't want to enter that loop immediately, right? We only want to enter that yielding loop the first time we ask for a value. We then implement our yield value, which just updates the current value to point to whatever the current value is that we're iterating over. Here, I'm just having us store a pointer to whatever the current value is, and that'll be some variable inside of the coroutine frame. For something like int, it would probably make more sense just to store the actual value, but if you've got something that's not copyable that you want to iterate over, then you can use a pointer. And then we return suspend always. And so that will mean that the co-await that's done on this function call will cause the execution of the coroutine to suspend. We then need to go and implement an iterator type in order to support use with that range 4. And so when we when we create the begin iterator, we say, okay, if we have a valid coroutine, then we resume execution of it. And if execution of the coroutine is then done, then this is an end iterator. Otherwise, we return a new iterator with the coroutine. The end just returns an end iterator. And then inside, we have to go and implement the operator ++ and operator star. I'll share the slides afterwards, and I can provide more information because I think I'm running short on time. But the end result is that we can, with very little code, go and implement a generator like this. This is the generator design pattern. There's lots of other design patterns that can be implemented using coroutines. So with that, I will have our little summary. So we've finally been able to add the last coroutine keyword here, which is co-yield, which is another way of suspending. It allows you to yield values without actually ending execution of the coroutine. And here is the mapping from the different coroutine syntax pieces to what the compiler generates for them. These are the design principles for the coroutines proposal. These come from one of Gore's slides. But they're designed to be scalable, right, to billions of concurrent coroutines. Since they're stackless, they don't maintain a stack for each coroutine. The coroutine frames tend to be very small, so you can go and start tens of thousands, millions of them, and you're not going to run out of address space, for example. They're efficient, so suspend resume operations are comparable to the cost of a function call overhead. Additionally, while I said before that the coroutine frame generally has to be dynamically allocated, it doesn't always have to be dynamically allocated. So in a lot of the examples we saw here, the compiler would be able to statically analyze the program and determine that, okay, there's no way for the lifetime of the coroutine to outlive the function in which it was constructed, so I'll just construct it using a local variable. And the compiler can actually do that. And I know Gore has worked on several optimizations related to that in our implementation. They're open-ended, so while there's a couple of library utility types that are provided for use with coroutines, they don't, basically the actual coroutines, all the interoperation with existing libraries, you get to, or library developers can implement themselves. So if you have existing libraries that you want to use with coroutines, it's very easy to do that. On the other hand, if you're an application developer and you're just using a bunch of libraries, you don't have to think about any of that, right? Like as long as the library developer has written those few lines of code for you and figured out how to make the bindings work, then you can just use it. And finally, it's usable in environments where exceptions are forbidden or not available, as we discussed. So I have a few references here. There's a few talks that are all available on YouTube, including another version of this talk that I gave in December in Berlin. And with that, we have reached the end of the slides. So I am out of time, but I am happy, like during lunch, to answer any questions that people have, or if you want to rant and whatever. But yeah, we should save that for lunch. So.
Facciamone un paio, poi tanto c'è anche il panel più tardi. Vai. Where is the customization point for the allocation of the coroutine context? Because I see the compilers generating a new, you said it's possible to overload, but I do not see any section where this could be possible.
Yes, so I said that the allocation behavior could be customized. I did not show how it is customized. For that, you will need to look at the specification, which is actually very easy to read for the most part. This, I think, is the latest version of the document. If you just search for that number, you'll find it. And I forget what exactly is the function you need to specialize or overload. But basically, you just provide your own allocation functionality.
Un'altra?
I have a doubt about the pattern. Where do you think that the coroutine could be really useful? And do you think that the coroutine could be used, for example, with thread together or with classes? Or where do you think that is the best usage of a coroutine in a complex system or software, and when, for example, there are heavy tasks that have to be performed?
Sorry, I think I missed the first part.
Yeah, the first part is about the usage of the coroutine in the design pattern, for example, and where is the best pattern? Where do you think that coroutine could be used?
I think there are, I guess I would say, I think there's a lot of patterns that lend themselves very well to usage with coroutines. Certainly any kind of state machine design can be simplified. Yeah, I guess it just really depends.
Suppose, for example, in the past I worked in a project where I have to extract data from a big database, and from them I have to create a 3D model, really complex, a lot of points and so on. And in order to do this kind of activity, we perform a lot of threads that are synchronized in different way and so on. Do you think that coroutine could help us to reduce synchronization point and so on? Because, for example, one thing that I noticed, and as you said before, coroutines are really useful for state machine and so on. But if I need something, for example, feedback when something is finished, for example, please extract this data, compute them, create a 3D model, and when you finish, advise me or create a notification.
Yeah, so I think I would answer that by saying that there's two orthogonal things here. So on the one hand, switching from a model where you have dedicated threads, doing dedicated tasks and waiting on each other, to a model where you have continuation passing, right? Where instead of saying, signal me, raise an event, or wake me up, when you're ready, instead of that, having a way to say, when you're done, call this function, or put this this task back into my thread pool or onto my thread that's running operations. Like switching to that sort of model can definitely lead to efficiency improvements in many cases. And then coroutines don't help you, I guess I would say they don't necessarily help you move to that model, but they make it easier to write code in that model. So in that sense, it does make it easier to move because you have to write simpler, easier code. But they're like, you don't need coroutines to move to that model. They just make it easier.
So, maybe I can help you because I have some sample later with coordination among tasks with when any and when all, for example, that can trigger a new task as soon as both or one of the tasks are completed. So there is a kind of synchronization there. And then you just co-await the resulting task. So in this case is something that is not relevant from the coroutines point of view, but can help in any way, and you take advantage of the coroutines to simplify the code.
Okay, thank you.
Excellent. Thank you very much.